Hello everyone, today we've got another video on simple harmonic motion. This video will be covering aspects of the timing of simple harmonic motion systems, and I'll be applying this to the cases of a pendulum and a mass spring system in order to derive the formulas for their periods that appear in the IB Physics data booklet. This video is applicable to IB Physics, but is also applicable to all boards and kinds of examinations of physics you would see that cover this topic. So if you're new here, welcome to Watch Me Do Math. Please subscribe if this video helps you and share it with your friends, for there are new videos every Tuesday, Thursday, and Sunday. Let's begin. So you may recall from the previous 3 videos on simple harmonic motion that there is one sort of fundamental rule about the motion that underpins it all, and that's the fact that A is proportional to, the acceleration of the body is proportional to the negative of the displacement of the body from some equilibrium position. So what does this mean in real terms for us? Well, we usually write this equation as acceleration is equal to minus omega squared x, where x is the displacement vector and omega is the angular momentum of the body. Notice how the body is not actually going circular motion or moving through any kind of angle per se, but it is called angular momentum because it describes how far along the body, or it describes the rate at which the body moves through a sine wave of displacement. There is a mathematical reason that this might be likened to circular motion as well, but intuitively it's because the body's up and down motion is the same as the up and down motion of a body that is moving in a circular orbit. If you think about it, because the equation for its displacement with respect to time is the amplitude times a sine wave So you might see how this is the vertical component of this velocity. For if this angle was the input angle to the sine function, then this would have some vertical displacement, the sine thing, r sine theta, where r is the amplitude because that's the highest and lowest it can possibly be. So anyway, let's get rid of all this. We want to focus down on the ideas that underpin the motion of the pendulum and the mass spring system. So going back to this omega quantity, when we're investigating these physical systems, this mass spring system and pendulum, we might often find that the system obeys something that is or can be approximated to Hooke's law. That is, the force on the body in question in the system is proportional to and the negative of the displacement of the body from that equilibrium position. This F equals kx equation often applies to springs, but can also be applied to any body in simple harmonic motion simply by the fact that force is going to be proportional to acceleration with mass as the parameter, meaning F is equal to ma. We've got this familiar equation where a is minus omega squared x. So you can see how F is equal to minus kx, or actual investigation of a particular system that undergoes SHM, or simple harmonic motion, might be related to a is equal to minus omega squared x. this equation in the sense that the both of them come to the result that F is equal to ma, or F is equal to minus m omega squared x. So I'm just going to make my pen a little bit thinner. If F is equal to minus m omega squared x is equal to, if these two equations are equal, then that means k, the constant of proportionality between the force experienced by the body and its displacement, is going to be equal to m, the mass of the body, times omega squared, the angular velocity of the body, through the sine wave. And omega, which is an important quantity from which we can derive other things like the frequency of the oscillation or the period of the oscillation, is going to be equal to, well, dividing both sides by the mass, we get k over m is omega squared, and omega is equal to the square root of k over m. And one point I want to really stress is that when you think of omega as a angular velocity, one thing that some teachers do is they'll describe it as, oh, it's used because it's similar to circular motion. But I want you to think of it as how far it has progressed through the sine wave of its displacement that it will inevitably progress through. As in, oh, you can say that it's at the angle pi over 2. It's at this point in its sine wave of displacement with respect to time. It doesn't necessarily say anything about where it might be in a circle, or where it might be in terms of bearings with respect to a particular point in the real world, but instead it refers to how fast does it move through a sine wave. If the start of the sine wave is 0 radians and the end of the sine wave is 2 pi radians, radians being a sort of measure of progress through a sine wave, omega is how fast it moves through that sine wave. So in this case, where k is the constant of proportionality between the restoring force and the displacement from the equilibrium position, omega is going to be equal to the square root of k over m, where m is the mass of the body in question. And so you may remember from circular motion a few things about the period and frequency of circular motion, or not. But anyway, in this video I'm going to help derive them for you. So we are interested in a couple aspects of this motion, that is the frequency of the motion and the period of the motion. The period of the motion is the time that the mass might take to perform one complete oscillation, or that is move through 2 pi radians of a sine wave. While the frequency of the motion is the number of oscillations that takes place per second. So first, let's think about the frequency, because this is more simply related to the angular momentum. If the angular momentum describes how many of 1 radian of the sine wave, if this is 1 rad, then angular momentum describes how many of these do we go through each second, whereas frequency says how many of the entire sine wave unit, how many of the entire 2 pi radians do we go through every second. So in that sense, omega is 2 pi f. It is 2 pi times f, because if we go through the entire sine wave f times every second, that means we are going through 2 pi radians every oscillation, and f oscillations per second, which multiplies out to 2 pi f radians of a sine wave per second. And that's sort of the stage of oscillations, how we're moving through the different stages of an oscillation. So one key equation is that omega is equal to 2 pi f. Another thing to look at is that t is equal to 1 over f. This is a very, very definitive property of periods and frequencies that relates them to one another. The period is measured in seconds because it's, for instance, if I let a mass go when it was attached to a spring and it went down and up and down again back to the center over 3 seconds, then I'd say its period was 3 seconds. And if it's taken 3 seconds to move through one complete oscillation, then that means it's gone through 1/3 of an oscillation per second. Likewise, if it was n seconds to complete one full oscillation, I would have gone through 1/n oscillations per second. And frequency is the number of oscillations per unit time that a body is going through, or anything is going through, in fact, in terms of waves, which leads us to the finding that period is naturally going to be equal to 1/frequency and vice versa, or frequency is 1/period, because if it takes t units of time to do something, then 1/t units of that thing are accomplished in each unit of time. And in this case, that thing is moving through one complete oscillation of simple harmonic motion. So that's all very well and good. How do we get to discovering the period of a particular thing in simple harmonic motion? Well, if you remember, the period is equal to 1/frequency, and the angular momentum is equal to 2 pi times the frequency. So given that angular momentum is the thing that we can most directly get to from our experimental observation of the body moving up and down, given that it's so closely related to the force, then we'd preferably have an expression for t in terms of omega. I keep saying W, that's a pretty bad habit because they're different letters, different languages. Anyway, so if W is 2 pi f, that means f is going to be W/2 pi, or the period is rearranging to take the reciprocal of f, 2 pi over omega. Another way you can think about this is in terms of regular speed, distance, and time. This t is 1/f is, you can kind of think of it like a rearrangement of s is equal to ut, because in this case s is one oscillation. You move through one oscillation of oscillating, and u is the speed in oscillations per unit time, or rather frequency, and t is the time taken to go through one oscillation, the period. So if this distance, or rather this progress through oscillations, is 2 pi radians of oscillation, then the speed at which something might go through one period of, pardon me, the time it takes for something to go through one period of oscillation might be, to go through one radian of oscillation would be t/2 pi, because that's 1/2π of an entire oscillation. That's the time taken, and so this becomes a really 1 radian rather than one whole oscillation. 1 radian is t/2 pi units time to accomplish, and this is accomplished at rate of progression, or kind of speed, but not really, if you will, of omega, the angular velocity. So it results directly from this, that 1 radian is accomplished by moving at angular velocity omega for a time of t/2 pi, that the period is equal to 2 pi over omega. This is just an algebraic rearrangement that you need to do. So the period is the time taken to move through 2 pi radians of oscillation, where radians is now sort of functioning as a unit of oscillation, divided by the speed at which you're moving through each radian of oscillation, omega radians per second. So that's why t is 2 pi over omega. Let's see what else we can find out about now the mass spring system, because this is the next topic of our video, and probably the easier one than the pendulum to look at. So if t is equal to 2 pi over omega, and we've established earlier that omega is equal to, what was it? If we look down here, omega is equal to the square root of k over m, where k is the constant of proportionality between the force and the displacement, the restoring force to the equilibrium and the displacement from the equilibrium. Then we get that the period is going to be equal to 2 pi divided by this square root term. And if we distribute this square root into the k and the m, we split it up, we get t is equal to 2 pi over the square root of k, which is over the square root of m. Or this is equal to 2 pi root m over root k. And if you prefer to write this in a more simple form, t becomes 2 pi times the root of m over k. And that's where that formula comes from for the period of a mass spring system. If you want a way to remember this easily, you know that it's 2 pi something because it's got to do with sort of fake circular motion or simple harmonic motion. You know there's a square root somewhere that's easy to remember visually. And you can say that this m looks sort of like a spring. And since the spring is the most important part of the mass spring system, or its mass spring system, this is on top and k is on the bottom. But really you could make up your own thing that might help you memorize this, or you can straight up put it into Anki or another flashcard software if such a competitor might even exist to memorize it completely. So now let's look at the pendulum system. If we draw it out here, we've got this pendulum with some tension T affected by some tension in the rope T acting on this bob, which is also affected by its own weight mg. So say the pendulum is at this position with angle theta from the normal. The pendulum is not moving in the radial axis, so it's not moving any closer or further away from the pivot, perhaps on the ceiling, but not necessarily so. So that means if we were to draw the free body diagram of the pendulum's bob, then this tension here would be equal to whatever component of the weight is in this direction. So if we model the weight, this downward force, primarily downward force, as a combination of these two vectors of forces, one in the opposite direction to t, and one over here, then you would find that in terms of theta, looking at this triangle here, where the hypotenuse is mg, this force towards the center of position, given a displacement away, is mg sine theta, where the tension is mg cos theta, but this is not relevant to our investigating of the situation. So if the restoring force, F, is going to be equal to mg sine theta, then how do we get it in terms of the displacement from the equilibrium? Well, if you consider the formula for the arc length of a sector, this displacement from the equilibrium is going to be just how far it's moved along here. So if it's got this radius r, which is equal to L, the length of the pendulum, from the pivot to the center of mass of the bob, moved through this angle theta, then your displacement is going to be just theta L. So how does this help? We have sine theta here and theta L here. But this doesn't actually help us that much, because sine theta and theta are pretty difficult to interact with one another without approximation. For instance, we might say, oh, f is equal to mg sine x over L. But that doesn't do anything for us directly. Although this is mathematically correct, it doesn't help us with the problem. So what we do is we use the small angle approximation, where theta is equal to sine theta in radians for angles that are close to 0 in absolute value. This approximation gets a little worse with time, but it's not so bad that most reasonable pendulums, like perhaps drawn out to 30 or 40 degrees, aren't quite accurate with this approximation in mind. So using this theta is equal to sine theta idea, f is going to be equal to mg x over L, replacing sine x over L with just x over L, as we replaced sine theta with theta. F becomes mg x over L, or the restoring coefficient is mg over L. F is minus mg over L x. And so, if we get f is equal to minus mg over L x, then that means mg over L is basically our spring constant for a pendulum, even though it is approximated. So, as we know that the angular velocity of this system is going to be k over m, where k is mg over L, then we can cancel the mass as it shows up here and here, and we just get the angular velocity of this pendulum through the oscillation is going to be the square root of g over L. There's a couple points I want to raise here now. This is an approximation because the math we use to arrive at it is also an approximation. It may be possible to solve this as some kind of differential equation where a is equal to minus g sine x over L, or rather the second differential of the displacement with respect to time is minus g sine x over L. But I have no idea how to do this, and so we just approximate this down to, using the small angle approximation, a case of simple harmonic motion, which it kind of is. So if omega is this square root of g over L, and t is 2 pi over this square root, then by a similar process of breaking up the square root into its two parts and moving the root L on top because it's a fraction within a fraction, we get t is equal to 2 pi root L over root g. Or rather, the period for a pendulum is approximately 2 pi root L over g, where this approximation gets better as the angle of the pendulum swing approaches 0. So that's all I have today to teach you about simple harmonic motion. This is the end of the series for the time being, unless you want me to make one really big video combining all of it, which I'm unlikely to do unless several people request it. But anyway, this has been Watch Me Do Math. There are new videos every Tuesday, Thursday, and Sunday. If this helped you, leave a comment and share the video with your friends, as well as the channel itself. And until next time, thank you for watching.